4.2, so electromagnetic induction. So electromagnetic induction, by the way, these next couple of chapters and even the last chapter, I did some reading to prepare for this class. And actually what we are learning in your textbook is actually just a very surface level knowledge. So we're actually not going very deep into the subject, right? If you try to check on Google, try to learn about these subjects, you'll find out that these subjects actually go way deeper than what we're actually going to be studying in our class. But because I guess we don't have time, because these kinds of things you'd probably take a whole semester just to cover these topics, but obviously we can't spend a whole semester doing this. So basically consider this an introduction to electromagnetic induction and later on transformers. So some of the concepts that we will come in this chapter will actually not be fully explained by the textbooks. So just keep that in mind. So electromagnetic induction. So you look at the photograph. It's a picture of a musician. He's playing an electric bass. Okay, so those of you who have played electric bass or electric guitar, you know that on a guitar or an electric bass, you have something that's called a pickup, which are those little round, or I should say long things at near where you're plucking the strings. So the guitar pickup consists of 4 magnets. Well, it depends on what kind of pickup, and copper coils. So what happens is when you pluck a string, the vibration of the string causes this pickup to produce an electrical signal, and this electrical signal is what gets sent out to a speaker. And the process or rather the idea or the concept or the phenomena that causes this electrical signal is what we call electromagnetic induction. Now, there are no batteries in this thing. So the question is, how does electromagnetic induction produce an electric current without the use of dry cells? So basically what's happening is, how does this device turn the vibrations of a string without any dry cells? It turns the vibration of a string into an electric current. Basically, it's turning kinetic energy into electrical energy. So how does that happen? So here's the idea. When a piece of copper wire is moved across magnetic flux, okay, so there's a magnetic field, and the magnetic field is going through this copper wire. And when we move this copper wire through this magnetic flux, it produces an electromotive force. So we learned previously what electromotive force is. So that it's the energy, that moves one coulomb throughout a circuit. An electromotive force is induced in the wire. This phenomenon is known as electromagnetic induction. Now, if you take this wire that is being moved across the magnetic flux, and we create a complete circuit, and we connect this circuit to a galvanometer. So a galvanometer is a type of device that is used to show electric current. You'll notice that the needle starts to move just a little bit. So something like this. So an electromotive force is also induced in wire if the magnet is moved towards the stationary wire, as shown is in figure 4.19. So let me just show you the few pictures here. So here's a picture. So you have the copper coil, and just by moving the magnets either towards or away from this copper coil, you actually produce EMF. And remember that EMF is measured in voltage. So what is happening is that there is a creation of voltage, or there is a creation of potential difference, right? there exists a potential difference because of the way the magnetic field interacts with the copper wire. Now, so when a bar magnet is moved towards away, the turns of the solenoid cut the magnetic field line. So what happens is, we know what the magnetic field lines are, right? And when you have these wires basically it goes through or it cuts through ataupun dia pintas ini garisan-garisan medan magnet. And so it's this action that causes the EMF to be produced. So if we create a complete circuit like this and connect it to a galvanometer, you'll see the needle start to move, right? And the movement of the needle will correspond to the movement of the magnet. If you move the magnet towards, it will go one way. If you pull the magnet away, it will go a different way. So it shows the ends of a solenoid are connected to a galvanometer to form a complete circuit. The induced electromotive force will produce an induced current in the circuit, and the galvanometer pointer shows a deflection. So this is the basis of how electromagnetic induction works. By the way, the word induced, if you're wondering what is an induced current. So an induced current means that there is an action that creates this current, and you are the one who creates this action. That's what the word induced means. You are the one, or you create the action that causes it. That's what the word induced here means. Yes. Okay, so is there a formula to calculate the? Well, okay, thank you for bringing it up. We will be going into that. You mean the formula for calculating the magnitude of the current? Is that what you're asking? Okay, so all right. I'm sure there is. That's not being touched in the textbook. But what we will be looking at today is what are the factors that affect the magnitude of the current. Okay, so that will come a little bit ahead. So where was I? Yes, so electromagnetic induction is the production of an induced EMF or electromotive force in a conductor when, okay, and these are the keywords, when there is a relative motion between the conductor and a magnetic field. So you have a magnetic field and there is a conductor. So either two things are happening. So if this is the magnetic field and this is the conductor, either the conductor is moving and so there's relative motion, or is the magnetic field or the magnets that are moving relative to the conductor, or both are moving but at different speeds. Either one of those causes causes EMF to occur. Or the other thing is when the conductor is in a changing magnetic field. So maybe none of them move, but the magnetic field changes, gets stronger and gets weaker over time. That also causes a EMF to occur and causes electromagnetic induction. By the way, this concept is used a lot in any sort of electronic devices that are meant to create audio. So for example, guitars just now, when the string vibrates up and down, it produces EMF. But because the string vibrates up and down and it also gets faster and slower, the amount of electric EMF that it produces changes over time. And so the way the guitar pickup works is that it detects these changes, and when it gets sent to these speakers, the different changes in electricity and current causes the sound to get higher or get lower or softer or louder. So that's how these are how the principles of things like guitar pickups and microphones works. All right, so this is what Henry was asking. Is there a specific formula? Is there a specific formula that we can use to calculate the magnitude of the induced EMF? Okay, first of all, yes, there is. However, it's quite complicated because, and our textbook actually doesn't touch on this. It doesn't even give the formula. The reason being, there are so many different there are so many different no, I shouldn't say so many. Our text gives three factors. So the main three factors are speed of the relative motion between the magnet and the conductor. So how fast is the difference? The number of turns of the solenoid. So when you have a solenoid, how many turns do you have? And of course, how strong is the magnetic field? So if it's just a straight wire and a magnet, then you only have to deal with only two different factors, which is the speed of the relative motion and the strength of the magnetic field. So when the speed of the relative motion increases, the amount of EMF produced also increases, which means you produce a greater current. So if you move the wire faster, you produce a greater amount of current. Second one is the strength of the magnetic field. So if you have a stronger magnetic field, then you also produce a stronger amount of EMF, and therefore creating a stronger current. Now, if you're using a solenoid, meaning to say you're using a coil of wire, then it's still the same as just now. So you calculate the speed of the relative motion, the strength of the magnetic field, and the number of turns of the solenoid. So you have one extra factor to deal with. Now, the other things that make this a little bit more complicated is you also have to take into consideration that usually the speed is always changing. It's always going up and down. And you also have to take into consideration how many times does it cut across the magnetic flux, right? And so because of these things, it's actually quite difficult to come up with a specific formula. I would imagine it will be difficult, but we can somewhat control using these three factors. Like I said just now, so the magnitude of the EMF also increases if more magnetic lines are cut in a certain period of time. Meaning to say, if you cut more magnetic lines, you get more EMF. If it moves fast but only doesn't cut that many magnetic lines, then you actually create a smaller current. So Faraday's law states that the magnitude of induced EMF is directly proportional to the rate of cutting of magnetic flux. So actually, let me just, since Henry was asking, we might as well take a look at Faraday's law. Let me just open up a picture here. Let me just show you what Faraday's law is. Alright, so that is Faraday's law. This here is Faraday's law. So voltage generated equals negative N over, all these different factors that you have to figure out. Which isn't, and this isn't actually going to be, don't worry if you find that, if that looks complicated, it's okay. That's not in your textbook, so it's not a formula that you have to memorize. Let me show you another picture. Let me just zoom into this just a bit. So Faraday's law, where N equals number of turns, and we have to take into account the magnetic flux. We have to take into account external magnetic field. We have to take into account the area of the coil. So there's a lot of things. And some of these things, the reason why we're not going to touch the formula for Faraday's law is because there are a couple of things that we haven't studied and will not be studying in Form 5. At least I don't think so. Like magnetic flux and external magnetic field and all those kinds of things. So yes, there is a formula for us to there are formulas that relate to the magnitude, but that is beyond the scope of what we will be studying in Form 5. So the important thing is you remember these main factors. Yeah. So speed of relative motion, strength of the magnetic field, and if you're using a solenoid, the number of turns in the solenoid. Direction of induced current in a straight wire and solenoid. So the other thing that we need to consider is what direction will this current be. So when we have a magnet moving and cutting through magnetic lines, will the current be going in one direction, or will the current be changing directions, and which direction will it be going in? So there are two situations where we might that we could possibly study. So the first situation is when we're dealing with a straight wire, and the second situation is when we're dealing with a solenoid. So in these two different situations, we actually have two different laws or two different rules that we can use to help us determine the current or direction of the induced current. So for a straight wire, we use Fleming's right hand rule. So it seems like Fleming and left and right hands always go together. He always has a rule using left and right hands. So the direction of the induced current in a straight wire can be determined by using Fleming's right hand rule as shown in figure 4.26. So this is the picture. And so if we were to take our right hand and we use our first three fingers, so thumb pointing up, index finger pointing forward, and middle finger at a 90-degree angle from the first two fingers, we can use that as a guide to help us remember where everything is going. So if the wire is going this way, so the motion of the wire is going this way, the magnetic field will be going where the index finger is. Okay, it's going in this direction, meaning to say from north to south. So north to south, and middle finger index current, the current will be flowing in the direction of the middle finger. So you can see it in action here. So in the first example, let me just zoom in to it. So for example, if the direction of the wire is up, and you can compare this with your right hand, when the direction of the wire is going up, the magnetic field is going in the same direction as your index finger, and like I said, from north to south, and the current is going in the direction that is 90 degrees away from those first two lines following your middle finger. Okay, if you turn it upside down, and then you have the same idea. Or actually no. By the way, you should keep in mind, by the way, direction of the Fleming's right hand rule is the thumb is the direction of the motion of wire. So if you have a situation like this where it's the magnet that's moving, you have to think about the direction that the wire is moving. So since the magnets are going down, it's the same as the wire moving up, right? So in this situation, the direction of the current is actually the same as this one, because remember, we are dealing with relative motion. So in this picture, the second picture here, the relative motion is that the wire is still going up away, even though it's actually the magnet that's moving, but relatively speaking is the same as if the wire is going up. And so you have the same rule. So the wire is going up, you have the magnetic field line north to south, and you have the induced current. So that is when we are dealing with a straight wire. Now what about when we are dealing with let me just change the view. So what about when we are dealing with a solenoid or a coil? So then it becomes a little bit I wouldn't say more complicated, but we just have to be a little bit more careful. There are more factors to think about. So for a solenoid, then we use something called Lenz's law. So Lenz is the name of another scientist. So Lenz's law is used to determine the magnetic polarity at the end of the solenoid when current is produced. So that coil, that solenoid, also has its own magnetic polarity, and Lenz's law is what tells us what that magnetic polarity is, or where is north and where is south. So Lenz's law states that the induced current always flows in a direction that opposes the change of magnetic flux that causes it. Right? This might seem complicated. It's really not that complicated. Okay? Basically, let me remove my face so that you can see everything. Basically, whatever the magnet is doing, the solenoid will produce a magnetic polaroid that will fight the movement of that will try to fight the movement of that magnet. So for example, first example here. We have a magnet being pushed towards the solenoid. So when a magnet is being pushed towards the solenoid will try to fight that. So how do you fight and what you have here is a north pole, by the way. Okay. North pole. Which pole fights the north pole? Remember, north pole, same poles, same type, so north and north, they will try to push or fight each other. So this solenoid will try to stop the magnet from going towards the solenoid. So since it's a north, in this situation here, you have a north pole. It will cause a current that also produces another north pole. So north and north will meet, and it will try to fight, and it will produce that kind of electric current. And so you have an electric current that moves in this direction, in this particular direction. Okay? Same thing, if you try to push a south pole towards the south pole of the solenoid, I should rephrase that. If you try to push a south pole towards the solenoid will try to fight that pushing. So it will try to push back. And so it produces a current, and the direction of the current will create a south pole. Right? Remember that the south and north poles are determined by the direction of the current. So it produces a current that goes in the opposite direction so that it can create a south pole to fight the magnet. Now this is if you're pushing towards. What about, Yeah, this is the thing sometimes. There you go. What about when you try to pull away? Now, if you pull the magnet away, now don't get confused. When you pull the magnet away, this time it will try to fight it. So just now it tries to fight the magnet from pushing in. So it's trying to give a force that fights that. But when you try to pull it away, it also tries to stop the magnet from pulling away. And so what happens? It creates, this time when you pull it away, it tries to create a polarity where it tries to stop the magnet from pulling away. So if you pull the north pole away, it will create a south pole, and the current will flow in a certain direction to try and stop the magnet from pulling away. The opposite is also true. If you try to pull the south pole away, then the current that it induces produces a north pole to try and stop the magnet from being pulled away. So basically what I'm saying is the solenoid is always trying to cancel the action of the magnet. If you try to push towards it, it will also try to push back. But if you try to pull away, it will also try to pull back. It's kind of like a person who can't decide if he or she wants to be your friend or not. When you try to get closer, they push you away, but when you try to pull back, they try to pull you back. So, so by looking at which pole and whether or not you're being pushed towards or being pulled away, we can determine what kind of polarity and also the direction of the current that will be created. So basically, there are 4 different situations that are possible: A, B, C, and D. So finally, we get to the idea of direct current generator and alternating current generator. So basically, what a generator is we use the concept that we just learned earlier, electromagnetic induction, to turn kinetic energy into electrical energy. All right, so I forgot to put in the picture, but you can find the picture in your textbook. And basically, both of these devices, they use the turning motion to create to create current. However, depending on the type of contact and how you set up the brushes, remember we learned about brushless motor and brushed motor. Okay, depending on how you set the contacts and the brush and how you deal with the turn of the coil, it can either be a direct current generator, meaning to say the current only goes in one direction, or an AC or alternating current generator where the current is always changing directions. So I'll just talk about the similarities and differences. So similarities. So both direct and alternating current generator, both of them use the concept of electromagnetic induction. Okay, in both cases, coil is rotated by an external force. So you have to use some force to turn the coil. And in both cases, the coil cuts through ataupun dia memintas the magnetic field. So there's an electric flux. And EMF is produced in the coil. So because EMF is being produced, current is also being produced. So the difference are in one design, the ends of the coils are connected to a split ring. In the other design, the ends of the coils are connected to 2 slip rings. The two sections of the commutator exchange contact with the carbon brush every half rotation. So in a direct current generator, the 2 ends of the brush, they change, right? Since it's turning around, so it changes. Whereas in an alternating current generator, the slip rings are connected to the same brush, which means they do not exchange contact. And of course, the output, one outputs direct current and the other outputs alternating current. And that's basically everything for electromagnetic induction. So for electromagnetic induction, like I said, it's less about the formulas and more about the application of these different things. So these concepts, Lenz's law, Fleming's right-hand rule, factors affecting the magnitude of the induced EMF, those are the things that you are going to need to understand and to remember for your upcoming exams. All right, any questions? 1 or 2 questions before I continue to transformer? Okay, maybe later. Maybe some questions will come up later. Okay, so let's go ahead with the last topic for chapter 4, transformer. Now, when I say transformer, I'm not talking about the transformer in the movie. I would have loved to have a discussion about how we could create highly technologically advanced robots that can transform into different shapes. However, we're talking about a slightly less impressive type of transformer, but still a very useful type of transformer, which is an electric transformer. So the working principle of a simple transformer. I don't know the exact curriculum, but you should have already learned about transformer in RBT class. Kalau saya tidak silap lah. Okay. At least for us when I was a student, we would have learned about transformer in RBT class. So what a transformer does, it changes the current or it changes the voltage of an electrical of electricity. So we'll see these pictures later. Figure 4.32 shows the structure of a simple transformer, and figure 4.33 shows the flow map for the working principle of a simple transformer. All right, so what we have here is a simple transformer. Now, you might find this in something like an electric socket or a power adapter for something like a laptop, or something like actually a lot of electronic devices uses transformers. Actually, most of it uses transformers. So what a transformer does, well, let's look at what it looks like first. So you have the input and you have the output. Excuse me. And there is a difference in the number of coils on both sides. So one side will have more sides than the other. So the primary coil has a certain amount of turns, and the secondary coil also has a certain number of turns. And so what happens is, so first you have the primary circuit or the primary coils. So AC power supply produces an alternating current in the primary coil. The alternating current produces a magnetic field that changes in magnitude and direction. The magnetic flux from the primary coil is leaked through to the secondary coil through the soft iron core. The changing magnetic field induces an alternating voltage across the secondary coil. Okay? And we have a formula here where the voltage of the secondary coil divided by the voltage of the primary coil equals to the number of coils of the secondary over the number of coils over the primary. So what it does is that from one side to the other, it changes the voltage. Now, why do you need that? Well, let me give you an example. Right? Your computer. So your computer and my computer is not designed to take 240 volts. Right? Your socket has about 240 volts in it. That's the standard amount of voltage here in Malaysia. But a computer is not designed to take 240 volts. So before you can connect your computer to that, you need a transformer. You need a step-down transformer that takes this high voltage of 240, brings it down to something like maybe 12 or 15, depending on the type of electronic devices. If you try to take a wire, or if you try to take the wire of your laptop adapter, you cut it and you connect it straight to the cable, you're gonna fry your computer. Okay. If you notice, every single laptop cable usually has like a sort of black box, plastic box on it, or some sort of square. That's usually where the transformer is. That's where the transformer is. That's where the change of electric voltage happens. That's why your laptop needs to have that. Yes. Okay. I'm not so sure about parallel. In series, yes, you can do that. Actually, that's what they do. It's actually in the textbook, but they do use that for distributing electricity to houses. So usually they use both step up and step down transformers, which is basically the same as connecting it in series. In parallel, it's probably possible. I'm not sure what the effect. I mean, yeah, it seems possible since it's still a circuit, but I'm not exactly sure what the effect would be. That's something that I haven't studied yet, and that's also not touched in this chapter. In series, yes, definitely yes. All right, so ideal transformer. So what is an ideal transformer? So figure 4.34 shows an electrical equipment connected to the output terminals of a transformer. Yeah, so a transformer receives input power and supplies output power. Therefore, electrical energy is transferred from the primary circuit to the secondary circuit. So we have the power supply, which supplies a certain amount of voltage, and that certain amount of voltage, of course, also produces a certain amount of current. And we have the transformer with the different number of coils. Now, in this picture, it shows the same number of coils, but actually, there's always going to be a different number of coils. And so there is power being transferred from one side to the other, being transferred to the electrical circuit. And so this electrical circuit will receive a different amount of current and voltage. Now, what happens though is that in this transfer from one circuit to the other, some of the energy is lost. All right, a transformer operation experiences a loss of energy. Therefore, the output power is going to be less than the input power. All right, so the total amount, not all of the power from the input goes to the output. Some of it is lost through heat and other types of energy loss. So the efficiency of the transformer N, well, it's actually not N, but let's call it N, is defined as, okay, I typed that wrong, the output power divided by input power times 100%. So that's how you calculate the efficiency. So nowadays there are transformers with very high efficiency, so up to 99% efficiency. So an ideal transformer is basically the perfect transformer that does not experience any loss of energy. That is, efficiency equals 100%. So when you have this, output power is going to be the same as input power. It's going to be a 1-to-1 ratio, so you get a 100%. Therefore, the voltage times the current of the primary coil will equal the voltage and the current of the secondary coil. Now, in reality, this does not exist. Like we just mentioned just now, there is always going to be a loss of energy. It might be a very small loss of energy, but there's always going to be a loss of energy. So the question is, as engineers and as scientists, how do we increase the efficiency of a transformer? A lot of engineering, whether it's mechanical or electronic engineering, a lot of it has a very big thing in engineering is efficiency, where you want to make sure that the electricity or the energy source is being used as much as possible without losing the energy as heat or other types of energy. Right? So the working principle of a transformer involves processes such as the flow of current in copper coils, the change of magnetic field, and electromagnetic induction. So all of these processes cause loss of energy. Right? So all of these things, there is loss of energy because why? Copper coils. Copper has a little bit of internal resistance. Okay, a magnetic field is not stable. It keeps changing. Electromagnetic induction. Most of the energy is lost in the form of heat. So the efficiency of a transformer can be increased by reducing the loss of energy. So we try to reduce this loss of energy as much as possible. So what are the causes of energy loss and what are the effects? So these are the four main causes and the main effects. Let me remove my face so that it doesn't block. Okay, the first one is the resistance of the coils. So of course, the wire itself has its own internal resistance, and the other thing is that the wires are very long. So remember, we learned that the longer the wire, the higher the internal resistance. So when current flows in the coils which have resistance, the wires get hot, and so the heat of the wires causes heat energy to be released to the surroundings. So that's the first cause of energy loss, the resistance. The second one is eddy currents. So what are eddy currents? So the changing magnetic fields induces eddy currents in the iron core, meaning to say there are extra magnetic fields. And these extra magnetic fields, they interfere with the magnetic field that you want to use, and it also called these extra eddy currents also heat up the iron core. And same thing, iron core releases heat energy to the surroundings. All right, another thing, so hysteresis. This is where the iron core is magnetized and demagnetized continuously by the changing magnetic core. Right, so the energy supplied for magnetism is not fully recovered during demagnetization. So what happens is the electric current causes the iron core in the transformer to magnetize and demagnetize. However, when it demagnetizes, not all of the energy comes back. Some of it gets lost as heat. Okay, and last one is the magnetic flux produced by the primary current is not fully linked to the secondary coil. So some of the magnetic flux does not go or fully go to the secondary coil, but it leaks to other places. Now, I know that certain words here are not being explained in depth, and that's because, like I said, if we were to study this thoroughly, eddy currents and hysteresis, as those two are very long topics, so I guess they decided that we will not be discussing this in depth. But just as a simple way to remember it, eddy currents are extra magnetic fields or extra currents that causes heat. Yes. Are they named after a physicist engineer? Yes, probably. But so the important thing is that, well, actually, maybe not. Probably not, since it's a small letter E. It's probably not named after a physicist. It's just a technical word, a technical name. So yeah, anyway, just assume that eddy currents is, extra currents that aren't being used, and the extra currents, they heat up the iron core. And hysteresis is what happens when the iron core is being magnetized and demagnetized. So how can we reduce the efficiency of a transformer? So first thing we can do for the resistance of the coils, we can use thicker wire. So remember that a thicker wire has a lower resistance. Okay, for the eddy currents, okay, we use a laminated iron core that consists of thin iron sheets glued together with insulation glue. So we use insulation glue and thin iron sheets to reduce the amount of heating up, and also to try and reduce the flow of eddy currents. By the way, eddy currents is also sometimes used. Sometimes you want to have those eddy currents, because eddy currents, the idea of eddy current is what is used for an electric cooker. So I don't know if any of you have used an induction stove. So it's a stove that doesn't use fire, but rather it uses electromagnetic waves to cause heat and cook. That is being produced using eddy currents. That heat that you used to cook is being produced by eddy currents. So sometimes eddy currents also have its uses. For hysteresis, we use soft iron as the core. So the reason we use soft iron is soft iron doesn't use a lot of energy to be magnetized, so you lose smaller amounts of energy. And the last one, leakage of magnetic flux. The secondary coil is wound on the primary coil. So you put the two coils very close to each other so that you reduce the amount of leakage of magnetic flux. Is there a picture here? Oh yeah, wait. Alright, this picture actually shows the magnetic flux or the leakage. So if you see this, the blue dots, the blue line, not the dark blue line, but the broken blue circles. So you see that some of the magnetic flux is being leaked outside. That's what we mean by leakage of magnetic flux. Alright, so eddy currents So yeah, here you can see that some of the currents, instead of being in the copper wire, some of the current is actually happening in the pan. So in an electronic devices, you don't want this because that means that the electric current that could have gone to your electronic devices is being wasted somewhere else. However, when you're cooking, then actually having these eddy currents is a good thing because then you can produce enough heat to cook. So it's an interesting concept, an interesting way, being able to cook without using gas. However, it also means that if there's a power outage, then you won't be able to cook. So there are pros and cons to it. So yeah, a high frequency alternating current producing a magnetic field which induces an eddy current at the base of the pan. So the eddy current heats up the base of the pan. Alright, so uses of transformers in daily lives. So the following are some examples of machines that use step down and step up transformers. So for a step down transformer, like I was saying, your computer, especially a laptop, if you try to connect your laptop directly to the socket, your laptop would probably explode. So you have the notebook computer charger, which is why computer chargers always have that sort of black brick or black piece of plastic that's quite heavy. The inside is the transformer. Okay, we also have photocopy machines and things like a welding machine. And now we also have examples where we need a step up transformer. So we need to actually increase the voltage or increase the amount of current. So we have the microwave, things like microwave ovens, things like defibrillators. When a patient is having maybe cardiac arrest, you use a defibrillator to give an electric shock to try and wake that patient up. And X-ray machines, so machines that need a high amount of current or a high amount of voltage. All right, so finally, one example of a question. Okay, so the only formula that we really looked into was this two. So N equals output power over input hour times 100. That is the efficiency, and the voltage and current of the primary coil should equal the voltage and current of the secondary coil. So let's take a look at this question, and we will go ahead and let's look at the question first, and then we'll go ahead and do the solutions. So let me read the questions first. So a transformer that is connected to a 240 volt, so standard Malaysian power supply, supplies 27 watts of power. So meaning to say 27 amps per second at a voltage of 18 volts to an electronic equipment, as shown in figure 4.36. Assuming the transformer is ideal, meaning to say assuming there is no loss. So it's perfectly efficient. So the first question is A, calculate the number of turns of the primary coil. B, calculate the current in the secondary circuit. And C, calculate the current in the primary circuit. So what are the formulas that we need to use, and what are the numbers that we need to think about? So let's start with question A. Obviously, the solutions are in your textbook, so this is just basically us going through the question step by step. Okay, so calculate the number of turns in the primary coil. So which formula deals with number of coils? So let's go back, let's take a look. This formula right here. So if we were to write it on a whiteboard, so voltage of the secondary circuit equals the voltage of the voltage over the primary circuit equals to number of coils on the secondary circuit over number of coils over the primary circuit. So that's the formula that we're going to use. Excuse me. So now that we figure out what formula to use, we can go back to the question. All right. So now that we know that, now we just need to determine the values of everything. So voltage of the primary coil is given at 240 volts. And the secondary coil is also given. It's uh, 18 volts. All right. The secondary coil has 60 coils. And the primary coil is not stated. Not stated. All right. So now we have all the information that we need to answer the question. So we have the formula. We already know what is the voltage of the primary coil and the secondary coil, and the number of turns at the secondary coil and the primary coil. So just substitute everything in the formula. So 18 over 240 equals to secondary coil 60 over ns. So we don't know what is the secondary coil. So just move everything around. So we can just move everything around and we get a final answer of, once we move everything around, we get a final answer of 800. So 240 times 60 divided by 18 equals 800 coils. So a lot of coils. So hopefully this gives you an idea of how many coils are involved. Okay, we're not talking about a small number of coils, but we're actually talking about possibly hundreds of coils. Okay, because you need to take a big voltage and really turn it down to a smaller voltage. All right, so that is the first question. Let's go into the second question. Second question, calculate the current in the primary circuit. So now we're using a different formula. And this is a formula that we also already took a look at earlier, which is this formula right here. All right, so voltage times the current of the primary coil should equal voltage times the current of the secondary coil. So again, same idea, same concept. Let's go back to the question. Let's write down all the things that we need to find out. Okay, so what we know is, so we only need to find out of one side. So what do we have? So output power. So we know the output power is 24 watts. 27 watts. All right, so we know that V, so the power equals 27 watts. Right? So once we have calculated that, just substitute everything. Okay, Vs equals 18 volts. So substitute that into the equation. 18 times I equals 27. So I equals 27 divided by 18, which equals 1.5 amps. So that's basically the whole thing. All right, and now finally question or letter C, calculate the current in the primary circuit. So this is when we now compare the current in the primary circuit with the secondary circuit. All right, so this one we use the answer from the previous question. So, question C, we know that the power on one side, or rather, the voltage and the current on one side should be equal to voltage and current on the other side. And we know that the voltage and current on one side is, we just learned just now, we set the values of, well, actually, let's write that down first. Okay. From the previous question, we know that Vs equals 18, Is equals 1.5. And we know that Vp equals 240. Ip is not given. Okay, so we just substitute all these values into the formula again. Okay, so Vp times Ip equals Vs over I times Is. So let's put that in. So 240 times Ip equals 18 times 1.5. Ip equals 18 times 1.5 divided by 240, which equals to 0.1125A. So the actual current is actually very, very low. I don't know if you've noticed, but if you look at it carefully, the voltage and the current on both sides change when we have a transformer, but the relationship is actually kind of opposite. Because for example, in this transformer, the voltage from one side to the other side goes down. It goes from 240 to 18 volts. So the voltage actually gets lower. But you notice that the current actually gets higher. So on one side, in the primary circuit, there's actually a very low current, 0.1124 amps. But when it goes to the other side, it actually goes up. It increases more than 100 times to become 1.5 ampere. And so that's another thing with transformer. We also use it to change the amount of current that's actually happening. Okay, finally, last couple of slides. Electrical energy transmissions and distribution system. So companies like SESB and TNB here in Malaysia are very important because they obviously distribute electricity from power stations to consumers. So any power station, so SESB, TNB, Tenaga Nasional Berhad, Meralco in the Philippines, okay, they should use the same ideas. So we have the power station. So at the power station, you have a station that is actually producing 20 kilovolts, which, if you think about it, is a crazy high amount of voltage. 20 kilovolts, high voltage. All right, and in a high voltage, it goes down to a step-down transformer. Okay, so from 20,000 kilovolts, we go to 200 and that's a lot. 275 kilovolts. So we reduce the amount of current, but we actually increase the voltage. Okay, and then when we receive, so this is when we're transferring electricity over long distances. Now, distribution of electricity. So when we're ready to distribute it to the different houses, we use a step-down transformer to receive it. So we reduce it to 132 kilovolts. And then we have another substation. So we reduce it now to 33 kilovolts. And so for some industries, for some big factories, that's the amount of electricity they receive. Okay, and we might step down some more. For smaller factories, we might go down to 11 kilovolts. And then for houses, like here in Malaysia, 230 or 240 or somewhere around that amount. Now, some of you might be wondering, okay, why do we need to go up and down? Why do we need to change the amount? The reason is this, okay? We use the step-up transformer to increase the voltage so that the current becomes small. Remember, voltage goes up, current goes down. What this does is that it reduces the loss of electrical energy because there's actually less flowing happening. It's just a very high potential difference, but less. There's not a lot of flow happening, which means there's less loss in the form of heat. Now then, when we reach the houses, we use step-down transformers to decrease the voltage, okay, in stages to a suitable value for industrial and residential consumers. Okay, so different industries, different buildings, different houses are going to need a different amount of voltage. So that's why we use transformers. So this is basically using transformers in series, basically. And so that's how it all works out. That's why, for example, right outside a major residential area, you always see like this big box, or sometimes near a plant, there's this what looks like a big box. So that's actually the transformer. And if those transformers get broken, then you know that you'll be out of power for quite a while because those things take a while to repair. And that's basically everything in chapter 4. So let's see your questions. So can we teleport electrical power from power stations to houses and industrial buildings so that the loss is zero? So first of all, considering, let's assume that you know how to teleport. Let's assume that we've created a machine to teleport power. Okay? Obviously, right now we don't have the capability for teleportation. Some scientists think it's possible. It's very hard to say. But let's assume that we have teleportation devices. Okay, can we now just teleport electrical power from power stations to house and industrial buildings so that the loss is zero or almost zero? Okay, the thing that you need to consider is any teleportation device that you have is also going to use electricity. It's also going to use a lot, and it's probably going to use a lot of electricity. Any sort of teleportation device that you come up with is most likely going to use a high amount of electricity. So because the teleportation device is also using electricity and probably also going to have some sort of electrical loss, then in that situation, the overall amount of loss, there is still a net loss overall. Okay, so given our current technology, that's just impossible. But we're assuming that we even have the technology for teleportation. And even then, over a short distance, there is still going to be some loss, right? Because basically what you're doing is you're reducing the loss. And the other thing is that you still need to use a transformer to convert the energy from the power station to the houses and the industrial buildings. And as we also learned earlier, even a transformer itself also has some has some loss in power. So it's an interesting idea, but the loss will still not be zero. Yeah, it's a dream of scientists, by the way, to be able to use energy at 100%. All right, the ultimate not the ultimate, but the ultimate dream is that one day we'll be able to use the energy of the sun at 100% without any loss. Of course, that's basically impossible with our current levels of technology, but that's the dream. So yeah, it's an interesting question, and that's basically what these electrical engineers are thinking. How can I reduce the amount of loss? What can I do to make this entire system as efficient as possible? So thank you for the question. Any other questions? it can be theoretical, or it could be, explanation of the um, asking for an explanation of the things we've studied so far. I know, especially for the what is it? I know especially for 4.2, there are some things that are probably not explained completely. That's because basically the book does not have enough space to explain everything fully. Even if you try to Google eddy currents and hysteresis and other things, you'll see long, long articles explaining it, and even the videos are long, like 20 minutes long. So I guess they decided to just not give a very in-depth explanation on those concepts. All right, let me just stop the recording.